The purpose of this program is to explain the fault diagnosis procedures that can be applied to identify faults that may occur on any conventional diesel engine. The two engines that we shall be looking at are the Gardner 6LXB, which is normally aspirated, and the Leyland TL11, which is turbocharged. In both examples, the engine is fitted to a Leyland Olympian, which has a rear engine vertical installation. Before proceeding with the fault diagnosis, let's briefly summarize the operating principles of the diesel engine and its fuel supply system. The fuel supply system consists of the fuel tank, the primary filter, the fuel lift pump, the main engine filter, the fuel injection pump, and finally, the fuel injector. The operating principle is as follows. As the fuel lift pump operates, a depression is created which lifts the non-return valve on the suction side and allows fuel to be drawn from the main fuel tank through the primary filter, which is responsible for collecting any large dirt particles or water which may be present in the fuel. The fuel then passes into the lift pump, and on the lift pump pressure stroke, this valve on the suction side closes, and the non-return valve on the output side opens, allowing fuel to pass into the main engine filter. This filter is responsible for the very fine filtration of dirt particles, ensuring a high degree of cleanliness before the fuel enters the fuel injection pump. In any fuel system, there is always a degree of aeration in the fuel tank. If this is allowed to pass to the fuel pump, the engine will run badly. To overcome this, a permanent bleed is fitted in the main filter to expel the small quantities of air back into the tank. This type of system is a low-pressure supply system operating from 1 to 4 pounds per square inch and is used on the Gardner engine. However, the Leyland has a high-pressure system. For example, the lift pump has a capability of 30 pounds per square inch, but the system working pressure is controlled by a pressure relief valve set at 15 pounds per square inch in the fuel injection pump. This is connected to a return pipe to the fuel tank. Now let us look at the final stages of the fuel supply. The basic function of the fuel injection pump is to pump fuel at a high pressure and at a regulated rate through the injector into the engine. The injector atomizes and directs the fuel into the cylinder. To complete the process, let's look at the operating principle itself. On this model, the sequence is as follows. On the induction stroke, the piston moves down the cylinder and the inlet valve opens, allowing air to flow into the cylinder. When the piston reaches bottom dead center, the inlet valve closes. As the piston rises with both valves closed, the air is compressed, generating heat. As the piston approaches top dead center, atomized fuel is injected, generating a pressure rise and causing the fuel to burn. As the piston goes over top dead center, a maximum pressure of between 1,300 and 1,800 pounds per square inch is reached. The piston is now on its power stroke. When the piston reaches bottom dead center, the exhaust valve opens so that as the piston ascends, the exhaust gases are pushed out to the exhaust system. Now let's take a closer look at the operation of these fuel injection components, as it's necessary to have a basic understanding if you're to carry out full fault diagnosis procedures. First, the fuel pump. The pumping plunger operates on a fixed stroke, determined by the camshaft in the fuel injection pump. The plunger has a helix machined into it so that rotation of the plunger increases or decreases the fuel injected per stroke. Let's look at the plunger in a part fuel condition. The plunger barrel has a supply port, so that when the plunger is at bottom dead center, Fuel at lift pump pressure is allowed above the plunger. Initially, as the plunger rises, the port will be cut off. As the plunger moves up, the pressure will rise, pushing fuel through the injector into the engine. This period of injection will continue until the lower edge of the helix uncovers the spill port, and at this stage, the pressure above the plunger collapses and injection ceases. If the element is now moved round to a full fuel position, you will notice that the plunger has travelled almost a full stroke before the lower edge of the helix uncovers the spill port, and so more fuel will have been injected. If the element is now rotated in the other direction, fully in the stop position, a vertical groove on the pumping plunger is in line with the port at all times. This is known as the stop groove, and in this position, no pressure can be built up above the pumping plunger so that no fuel is delivered throughout the stroke. In the outlet above the pumping plunger is the delivery valve. This is responsible for collapsing the pressure in the injector and pipe quickly at the end of each injection stroke, so that the injector needle, which we'll be discussing later in the programme, drops onto its seat to give a clean fuel cut-off, thus avoiding the injector dribbling, causing smoke. When pressure builds up above the pumping plunger, the delivery valve moves up against the spring. Initially, the mitered valve moves off its seat, and with further increase in pressure, the valve moves up further until the plunger section of the delivery valve clears the barrel. Only when this point is reached will fuel flow into the injector. At the end of the injection stroke, the pressure on the underside of the delivery valve collapses. The valve moves downwards and the plunger section sweeps down the barrel. This has the effect of increasing the volume in the injector line, giving a rapid collapse of fuel pressure. Now let's move on to the injector. This is in three main sections: the nozzle with the spray holes, the needle, and the spring. During the injection stroke, fuel enters the injector and acts on this area of the needle. Fuel pressure, usually between 125 and 235 atmospheres, builds up and moves the needle up against the spring, which allows the fuel to spray into the cylinder at high pressures. Because of these high pressures, the fuel is in an atomized state. Providing that the needle is a correct fit in the main injector body, a small quantity of fuel will pass between the needle and the injector body for lubrication and cooling purposes, and leak back through the small pipe to the fuel tank. Within the design of the injector, there is provision for adjustment of the main spring, either by screw or shims, to adjust the opening pressure of the injector. Needle lift can also be adjusted by using shims. Finally, let's briefly summarize the pressure and temperature in the diesel engine during the compression and power stroke cycle. Fuel is injected into the cylinder during the compression stroke, starting between 30 and 10 degrees before top dead center, depending on the engine type and specification, through to approximately 10 degrees after top dead center. Initially, when the fuel is injected into the cylinder on the compression stroke, the fuel burns slowly. However, as the piston ascends further towards top dead center, the rate of burning increases sharply, just before top dead center. Maximum pressure is reached just after top dead center when the piston is moving down on its power stroke, which is in the order of 1,300 to 1,800 pounds per square inch, depending whether the engine is normally aspirated or turbocharged. Peak cylinder temperature at this point is about 1,600 to 2,000 degrees centigrade. It will be appreciated from the diagram that if the fuel injection timing is advanced from the recommended, that the peak cylinder pressure will be closer to top dead center. This will generate higher peak pressures, which will subject the engine mechanical components to unnecessary stress and create possible failures. In addition, peak temperature will also rise, again increasing the risk of piston and injector failure. Now that you have an understanding of the basic principles of the diesel engine, we can look at the fault diagnosis areas. Many of the procedures applied will be similar to both the Gardner and Leyland engines. Where there are major differences, they'll be covered separately. The main areas of fault finding we should be looking at are the engine will not start, the engine down on power, black smoke emission, white smoke emission, and blue smoke emission. First, let's look at the engine will not start. A diesel engine requires both the correct supply of air and the correct supply of fuel to be able to start. But remember, there are different starting techniques for the Leyland and Gardner engines. Most diesel engines can be started by applying full throttle. This method applies to the Leyland engine. However, in the case of the Gardner engine, no throttle should be applied. If the throttle is applied, the advance retard mechanism would move to the advanced position, making starting more difficult, details of which will be covered later in the program. In extreme cold conditions, the Gardner engine has an excess fuel device which is manually operated and allows an additional quantity of fuel to be injected during starting, and automatically retracting once the engine has started. The Leyland engine, which has a Friedman and Mayer fuel injection pump, has an excess fuel device which is automatically engaged every time the engine is started and disengages at approximately 250 RPM. You should be aware that in general terms, for the engine to start from cold, it must reach approximately 350 degrees centigrade on the compression stroke. This temperature will only be generated if the engine cranks at 150 RPM with a compression of 400 pounds per square inch. If, for example, you had poor compression, or alternatively the cranking speed is reduced to 100 RPM due to either a starter or battery fault or the use of too heavy a grade of oil, this temperature may not be reached and it's unlikely the engine will start. Next, check if there is smoke or no smoke coming from the exhaust during cranking. If there is smoke, then fuel is being injected into the engine. In the case of the Leyland engine, check that when the throttle is depressed, the throttle control lever on the fuel pump moves to the maximum position against the stop. To carry out this check on the Gardner engine, to see if the rack is moving to the full fuel condition, move the stop control lever to the stop position and slowly release. During this operation, check that the rack return spring, which is located behind the fuel injection pump close to the excess fuel device, is moving approximately 3/4 of an inch. Whilst in the area of the fuel pump on both engines, operate the stop control mechanism and check that after initial operation it returns to the run position. If it does not return fully, this can affect the full fuel position. The other factor which could affect starting is injection pump timing to the engine. The engine must be set to injection on number 1 cylinder. On the Gardner, to determine the stroke, rotate the engine until this set screw comes into view. Continue rotating the engine until the injection mark on the flywheel, or on later models the crankshaft pulley, are aligned accurately. Now check that the alignment of the two marks on the coupling are in line. If they're out, slacken the bolts on the fuel pump camshaft coupling and rotate until they're in line and retighten the bolts. To complete the check, remove the front bank dust cover, uncovering the fuel pump ports, and move the throttle to the fully open position. Now, the scribe lines on number 1 port should be in line. If they're not in line, do not attempt to correct it by altering the main drive coupling, as the pump requires specialist attention to correct a phasing error, details of which are in the support notes. To check the timing on the Leyland engine, we must again set the engine to injection on number 1 cylinder. Rotate the engine until this scribe mark on the fuel pump coupling comes into view. Insert a timing rod into the flywheel through the inner hole and slowly rotate the engine until the rod engages into the timing hole in the flywheel. The scribe line on the pump flywheel should now be in line with the pointer. A secondary check can be carried out by a method known as bump timing. Slacken the clamp bolt on the main clamp coupling and move the pump coupling back approximately 1 inch. Carefully move the coupling in the drive direction until a resistance is felt. This is now the point of injection. Care should be taken not to force the flywheel past this point, as it will over-advance the engine. Retighten the clamp bolt and remove the timing rod. This series of tests should have identified any faults on the Gardner engine. But in the case of the Leyland, because there is no visual means of checking for full rack movement, if the fault still persists, the pump should be removed for servicing. If we had a no-start condition with no smoke, this indicates that no fuel is reaching the engine. There may be a failure in the supply of fuel from the tank to the fuel injection pump, or there may be a failure in the delivery from the fuel injection pump to the injectors. Before checking out the fuel system, there are simple external checks that can be made to make sure it's not a fuel injection control pump problem. First, check that the stop control lever is moving correctly and not sticking. In the case of the Leyland engine, check for full throttle. If the basic controls are in order, check for free movement of the rack. In the case of the Gardner engine, this can be checked visually, as seen earlier, for movement. But on the Leyland engine, it can be checked by operating the stop control lever. A slight resistance should be felt as it's moved to the stop position, and the lever should return as it's released. On this demonstration model, this is the movement you get when operating the stop lever. If you're unable to move the lever towards the stop position, this indicates that the rack has jammed. But in either engine types, if the rack has jammed in a no-fuel condition, the engine will not start. If all these checks prove correct, carry out a check on the fuel supply system. First, establish if fuel is being delivered from the lift pump. This can be done by disconnecting the outlet pipe and operating the lift pump by hand or by engine cranking. If there is no fuel, the fault may be in the lift pump, a blockage in the primary filter, or an air leak in the pipeline from the lift pump to the tank or the filter itself, or a blocked vent. Now let's carry out these tests. First, check if fuel is being delivered from the lift pump outlet. If no fuel is present, remove the primary filter which is near the fuel tank. Remove the filter and clean. A replacement sealing ring should be fitted, but before replacement, check that all fuel connections are tight and inspect the pipework from the tank to the lift pump for holes, particularly where they pass through clips where they may have chafed or been restricted. Remember, it's sometimes possible for air to be drawn into the suction side of the system without any visible signs of fuel leakage. Although the Olympian has a large tank vent, other vehicles may not. So check the tank vent, because if this is blocked, it can not only stop the fuel supply to the engine, but can cause the tank to collapse. If, after these tests, there is still no fuel at the lift pump outlet, then there is a fault in the lift pump. But if there had been fuel at the lift pump, check to see if air is present. First, at the main engine filters, then the fuel injection pump. If, during bleeding, air was present and the engine now starts, this indicates that there was air in the system. This could be due to air being drawn into the suction side or a restriction or blockage in the permanent bleed of the main engine filter. This is located in an adapter at the head of the filter. If no air is found in the system, disconnect an injector pipe, crank the engine and check for fuel. If there is no fuel present now, then the fuel injection pump is faulty. But before concluding in this area, let us look at the components on a Gardner engine. If when the lift pump is operated, no pumping resistance is felt, before suspecting a faulty pump or suction problem, rotate the engine a half turn, as the cam on the fuel injection drive shaft may be holding the pump at the top of its pumping stroke. The main engine filter is at the front of the engine, and this is the permanent bleed. These are the bleed points on the fuel injection pump. Now let's look at two typical fault conditions that can occur on the fuel system. Firstly, if the vehicle is operating satisfactorily during the day but refuses to start the following morning until the system has been bled, the fault most probably would be in the lift pump non-return valves, allowing fuel to drain back to the tank, leaving a pocket of air in the filter and aerating fuel in the injection pump when attempting to start. Secondly, during severe cold weather conditions, if the vehicle initially starts and then stops, the most likely cause is in the primary chassis filter, where any water that has collected may have frozen, or the fuel waxed and blocked the filter. The next area of fault finding is where the engine power is down. First, listen to the engine to see if it's misfiring. If there is no misfire, check that the fuel injection pump is getting full throttle. In many instances, the sole cause of down on power is that the engine is not receiving full throttle, and it's therefore vital that this check is carried out carefully. This can be carried out by applying full throttle and check for firm contact between the fuel pump lever and its maximum stop position. To ensure that this contact is made, check that a 1.5 thou feeler gauge is nipped. Whilst the throttle is in this position, manually attempt to push the throttle control rod back. If this can be moved, reset the throttle linkage and check the air pressure. If everything is in order, check the operation of the stop control mechanism to make sure it's not partly engaged. Another area for loss of power is fuel starvation, which could be in two main areas, either in the fuel filters or in the lift pump. In the case of the fuel filters, the problem may be due to either the filters being blocked, certain filters incorrectly fitted, or finally, filters of an incorrect type being used. If there is any doubt in this area, replacement of the correct type of filter should be carried out. The lift pump could be down on pressure and delivery rate. Although both types of engine run at different pressures, the lift pump must always have capacity in excess of engine requirements. If we have fuel starvation problems, we can check the lift pump performance by disconnecting the return pipe to the fuel tank and with the engine running, observe the flow rate at idle and full throttle. If the flow rate slows down or stops when the engine is revved, this points to a problem in the lift pump. But if the lift pump is operating satisfactorily, check the fuel injection timing as described previously. If this is correct, the fuel injectors should now be removed and checked to see if they're the correct type and specification for the engine and for operation. On the assumption that the controls are in order, let's consider the items on the fuel injection system that can cause an under-fuel condition and a loss of power. This could, of course, be due to the fuel injection pump. But before removing this item, you should be aware that the injector also has a bearing on the fuel that is delivered to the engine. If the injector needle does not lift sufficiently, this will reduce the volume of fuel that is passed to the nozzles. On low delivery rates, if, for example, the injector was set to open at 200 atmospheres, the pressure will increase in the pump, the fuel line, and then the injector. The needle now lifts against its spring, and so fuel is delivered to the engine. In conditions of high fuel delivery, the injector needle and nozzle holes offer resistance, which causes the pressure in the fuel injection system to rise approximately by 3 times normal injection pressure, 600 atmospheres. But if the nozzle holes are too small or partially blocked, this offers an additional increase in resistance in the system, causing less fuel to be delivered and a considerable increase in maximum injection line and pump pressures. For these reasons, always check that the correct type of injector is fitted to your type of engine and that the holes are not blocked. Finally, if, after this, the engine is still down on power, the fuel injection pump should be removed and tested. Always remember that this fault down on power could be caused by conditions other than the engine, such as a fault in the braking system, causing the brakes to bind. Or if the vehicle is fitted with a retarder, this could be partly operative. But of course, these faults are covered in other programs. If we now look at the same conditions, but this time with a misfire, first check that there is no air in the system as before by bleeding the main engine filter and fuel injection pump. If all is in order, inspect the fuel injection pipes for any sign of leakage. Next, to identify on which cylinder the fault exists. With the engine running, release each of the injection lines in turn. And if the engine revs drop when a pipe is released, this indicates that the cylinder is in order. But however, if the revs do not drop, then the fault probably is on that cylinder. To find out if the fault lies either in the fuel injection pump or in the injector, disconnect the injection pipe and check whether there is fuel when the engine is cranked. If fuel is present, the fault is in the injector, but if no fuel is present, the fault is in the fuel injection pump. It may be that the control quadrant has slipped, leaving the pumping element in the no fuel condition, or that the tappet has seized at the top of its stroke. If both the fuel injection pump and the injectors are correct and the misfire is still present, then there is a major problem on that cylinder, such as a failure of the valve gear or a piston problem causing a major loss of compression. Some Gardner engines have individual priming levers fitted to the fuel injection pump, and by operating this lever fully with the engine running, the fuel feed to each cylinder can be isolated in turn to identify the misfire. Alternatively, this test can be carried out with the engine stationary. When pulling each lever back, a resistance should be felt and a squeak heard from the injector. If, however, no pumping resistance is felt on a lever, before assuming a pumping fault, rotate the engine half a turn, as the injection pump camshaft may be holding the pumping element at the top of its stroke. Should the problem persist, then there is a fault either in a seizure of the ram tappet, a loose pumping element quadrant, or a faulty injector. The next part of the programme will be dealing with smoke emission from the engine. And in order to understand the various reasons for these emissions, we must have a brief understanding of the operating principles of both engines. First, let's deal with the normally aspirated type of engine, of which the Gardner is an example. If this engine is running correctly, as the piston moves down on the induction stroke, air is drawn in from the air cleaner into the cylinder. As the piston moves up on the compression stroke, the air is compressed, fuel injected, and at a point just after top dead center, complete combustion takes place, forcing the piston down on its power stroke. As the piston moves up again, the spent gases are pushed out through the exhaust system. In the case of the turbocharged engine, of which the Leyland is an example, the operating cycle is the same. Air is drawn past the turbocharger and into the cylinder. However, on the exhaust stroke, the spent gases pass through the turbocharger to the exhaust system. Within the turbocharger is a compressor wheel on the induction side and a turbine wheel on the exhaust side, which are connected by a central shaft. The exhaust gases drive the turbine wheel, which drives the compressor wheel at speeds in the order of 80,000 RPM, generating a pressure in the inlet manifold. Thus, more air is pushed into the engine on the induction stroke. Because of this, more fuel can be injected into the engine, resulting in more power, but still maintaining complete combustion. A boost control is fitted to engines of even higher power outputs to limit the maximum fuel delivery at low engine speeds to avoid smoke. This is because, under these conditions, the air output from the turbocharger is low. As engine speed increases, so does the turbocharger speed and pressure, up to a maximum of 15 pounds per square inch at full load. During this pressure increase, the fuel injection pump is allowed to progressively deliver more fuel through to full power. Let's first look at the causes of black smoke emission on the normally aspirated engine. This is due to two main causes. Either there is insufficient air or too much fuel. For example, if there is the correct amount of fuel being delivered to the engine and there is a restriction in the air cleaner or intake trunking, this will result in the air-fuel mixture to the engine being over-rich, resulting in the engine being unable to burn all the fuel completely. Alternatively, if the air supply is correct and the fuel injection pump is delivering more fuel than it should, then again the mixture will be too rich, resulting in the engine again being unable to burn all the fuel. In addition, the injectors must both atomize and distribute the fuel correctly within the cylinders. Otherwise, incomplete combustion will again take place. The exhaust system must not be restricted in any way. Otherwise, the exhaust gases will remain in the cylinders, reducing the fresh charge of air on the next induction stroke, again producing black smoke. If you have a condition where there is black smoke and with poor engine performance, this probably indicates that there is an air restriction problem. But if the vehicle is pulling well, this will probably be an over-fuel condition. So let's consider the checks necessary on an over-fueling condition. On the Gardner engine, you should check that the cold start fuel device is not jammed in the excess fuel position. On the Leyland, of course, this is automatic and cannot be checked. Next, on both engine types, ensure that none of the fuel pump quadrants have become misplaced and moved to a high fuel condition. To conduct this test on the Leyland engine or the Gardner without priming levers, remove the fuel injection pipes, taking care not to bend them, and crank the engine. As the engine cranks, fuel will be visible on all the pump outlets. Move the stop control lever slowly towards the stop condition. All the outlets should stop at the same time. If, however, one or more outlets still deliver fuel, this indicates that they're in a high fuel condition. On some Leyland engines, there is a calibration scribe mark on the back of the fuel injection pump body, which should align with a corresponding scribe mark on the delivery valve retaining clamp. If these have been moved, the pump should be removed for recalibration, although in an emergency, reset the marks accurately. On the Gardner engine, remove the quadrant cover on the side of the fuel injection pump and check that the quadrant is in line with the mark on the barrel. If these are misaligned, reset the lines. If these checks are in order, before removing the pump for testing, check that the injectors are of the correct type and specification for your engine. For example, if the nozzle holes are too large, this will allow more fuel into the cylinders. The first stage in the test procedure for injectors is to check that the discharge pressure is up to specification. Next, ensure that the injector is atomizing the fuel correctly and not hosing, and ensure that no holes are blocked in the nozzle. To check the condition of the needle and seat, with a sustained pressure of approximately half discharge pressure, the nozzle should remain dry. Running the engine in an over-fueled condition, or with an injector hosing, can cause the fuel during injection to strike the cylinder wall, destroying the lubrication and causing high piston and bore wear. Overfueling also causes the peak cylinder temperature during the power stroke to rise above the designed running temperature. Both of these factors will affect the economy and reliability of the engine. Before replacing the injector into the engine, with a special tool, clean the injector hole and seat. If this is not done and the injector is forced into the hole, it may cause the needle to stick, and also if the seating is not cleaned, it could cause blow-by. If the engine you're working on has a sealing washer, this must be replaced or annealed. It's also very important, when installing an injector, to tighten to the correct torque specified. If this is exceeded, it may cause distortion of the injector body, causing the needle to stick, resulting again in hosing and dribbling. In severe cases, cracks could result in the cylinder head by the injector seating. If we had a condition where, with black smoke emission and the vehicle performance was down, we would suspect an air restriction problem. With both types of engine, an air restriction gauge is fitted, and if this indicates red, then it confirms that an air restriction problem exists in either the air cleaner or the air trunking to the engine. First, replace the air cleaner element and reset the depression indicator and road test the vehicle. If the problem still exists, an inspection should be made of the complete intake trunking. As on certain types of trunking, although it may appear to be correct externally, the inner trunking may have collapsed. If there is no problem to the air supply, check the injectors as described earlier in the program. In the case of the turbocharged engine, it's possible that the turbocharger may have seized, restricting the air to the engine, and it will also impede the exhaust gases, resulting in black smoke and power loss. To do a complete check on this unit, remove the intake trunking and exhaust outlet and check if the unit spins freely. Next, press the shaft, first in one direction and then the other, at the same time checking if the unit still spins freely. It'll be found that the shaft will rock on its bearings. This is not a fault, but check that the blades do not touch the housing when this is carried out, as if contact is made between the blades and the casing, this will slow down the turbocharger, resulting in air starvation to the engine. A visual inspection of the turbine and compressor blades should be made, as damage to these will throw the turbocharger out of balance, again reducing its speed. To conclude in this area, we recommend that the maintenance schedules for the air cleaner should be such that the depression gauge never shows red. If the indicators on the vehicles within your operation start to show red, then the filter maintenance change period must be shortened. Whilst in this area of the air supply, either during the fault diagnosis or maintenance as the air trunking is checked, be aware that the smallest of holes or a loose trunking connection can result in a large quantity of abrasive material being drawn into the engine, causing severe wear. Now we've been through the procedures where there is black smoke emission and checked for both overfueling and air restrictions. However, if we have black smoke and there is a misfire, the following tests should be carried out. With the engine idling, can you hear a knock or a chuffing sound from the engine? If so, proceed to isolate the fuel supply to each cylinder in turn, using either of the two procedures used earlier in the program. If the chuff stops when the fuel to a particular cylinder is isolated, then it indicates a fault in the fuel supply to that cylinder. But if it persists, then the fault is in a mechanical part of the engine, and before carrying out any major work on the engine, the tappet clearances should be checked for correct clearance. If the engine is fitted with a decompressor, this should be checked to make sure it's not partly engaged. If the problem is in the fuel supply, check that the pumping element has not moved to a high fuel position as described earlier. If this is in order, check the operation of the delivery valve and the fuel injection pump. Remove the fuel pipe from the outlet and move the stop control manually to the stop position and operate the lift pump. If the delivery valve is in order because it's retained in its seat, no fuel should pass. However, if the seating is damaged or the valve held off its seat by dirt particles, fuel will pass through when the lift pump is operated. If the delivery valve is faulty, this will cause the fuel injector to dribble and not have a clean cut-off. This will cause a knock and smoke, particularly noticeable at idle. If all is in order, check the injector, and if the injector has any damage to the nozzle or any parts missing, it's important before returning the vehicle to service to check the turbine wheel on the exhaust side of the turbo has not received any damage, as particles may have passed through to the exhaust system. Before leaving this area of smoke emission, let's look at 3 items which could cause the engine to emit severe conditions of black smoke, and in some instances not allow the engine to rev. Firstly, if the air trunking has collapsed, it will cause complete starvation of air to the engine. Secondly, if the turbo has seized due to bearing failure or blade damage, it will restrict the air supply to the engine and also restrict the exhaust gases from the engine. And lastly, although not always installed, an exhaust brake which jams in the closed position. The characteristics of this problem are that the engine would idle normally with no smoke. However, any attempt to rev will cause large quantities of black smoke and maximum engine revs will be severely restricted. White smoke emission is caused by 2 main reasons. The fuel injection timing may be excessively retarded, or the temperature reached on the compression stroke may be below normal, so that the fuel injected into the engine is not completely burned. First, is the engine misfiring or not? If it's not misfiring, check that the fuel injection pump is not retarded. However, if this condition is found on the Gardner, because the engine has chain-driven timing gears, it's important to check the correct adjustment of the chain. If it's slack, it'll cause the fuel injection pump to be retarded. The adjustment of the timing chain can be checked by decompressing the engine and rotating backwards half a turn. Now, by twisting the alternator drive shaft, any backlash will be felt, and if this is in excess of 1/32 of an inch, adjust the timing tension with this lever on the front timing cover. By slackening the clamp bolt, then the lever nut, move the lever in a clockwise direction till resistance is felt, and that the backlash has been reduced to 1/32 of an inch. However, no undue force is required when moving this lever. If all is in order with the timing, then check the injectors, and while the injectors are out, carry out a compression test. If, on the other hand, there had been misfiring with white smoke emission, isolate the cylinder by disconnecting the fuel supply, and if the white smoke stops, then there is a fault on that cylinder. You should check the compression and injector on that cylinder. If the compression is now in order, then the fault is probably a cam or cam follower in the fuel injection pump, causing retarded timing on one cylinder. Let's now look at conditions that could cause blue smoke emission. The only cause for this is the engine burning lubricating oil. On the assumption that the correct grade of oil is being used, check that the oil level in the sump is not above the maximum mark on the dipstick, as if this mark is exceeded and the level is too high, the connecting rods will dip into the oil and throw excessive amounts onto the cylinder walls, and in quantities that the oil control rings cannot cope with. This may be due, of course, to the engine being overfilled. Alternatively, it may be due to diesel fuel entering the oil system. Although there are many places this can take place, first inspect the injectors, leak-off pipes, the end plugs on the injectors, and there are many other areas where this can take place. For example, a faulty diaphragm on the lift pump. But this and other details are covered in the support notes. If the blue smoke problem still exists after these tests, inspect the cylinder bores, piston and piston rings for wear and glazing. With turbocharged engines, we must take into account fault conditions that can occur that will cause oil to burn. The turbocharger, while running, is fed with engine oil for lubrication, which is then returned to the sump. At each end of the turbocharger shaft, there are oil seals. Should these fail, particularly on the turbine end, oil will pass into the exhaust system and burn while the engine is under full load. If there is blue smoke emission, check if oil is present in the exhaust system. If there is evidence of this, inspect the turbocharger oil return pipe for any sign of restriction, as any restriction here will cause the oil pressure to build up in the turbocharger and push oil past the shaft seals. Finally, remove the exhaust outlet on the turbocharger and inspect the blades for oil. If it's like this, the turbocharger is faulty. When fitting a replacement turbocharger, always remember to charge the unit with oil. Otherwise, you may severely damage it during the first few minutes of operation. During this program, we've attempted to give you a guideline for both the Leyland and Gardner engines for possible faults that might occur. To assist you with the diagnosis, detailed fault charts are contained in the video program guide and the fitter's pocketbook. During these test procedures, always be aware of the possible danger points within the engine compartment: the ventilation fan, rotating drive shafts, fan belts and pulleys. Always ensure the area around the engine is clear before starting up, and do not run the engine with the air trunking disconnected. Always turn the isolation switch off and display a suitable notice if you're working on the engine. At any time, if there is any doubt on the procedure to adopt, you should seek further advice. In many instances, expensive fuel injection components are replaced unnecessarily for poor performance, when, for example, the fault may be as simple as the vehicle not receiving full throttle. The maintenance of air filters and the inspection of trunking is very important to avoid undue restriction of air to the engine. And it's important there are no holes or air leaks in the system, allowing dirt to enter the engine. Always use manufacturer's recommended fuel filters, as this is the only way you can be sure the filter will pass the correct volume of fuel and stand the operating pressure without disintegrating, particularly on the high-pressure lift pump systems, and give the correct amount of filtration to protect fuel injection equipment. Under no circumstances be tempted to tamper with the seals on the fuel injection pump, which controls the governed engine speed and maximum fueling of the engine. Otherwise, serious damage may occur. Remember always to adopt a logical approach when a fault condition arises, as this will save time and money. If you ignore the settings, the replacement parts, or disturb fuel or governor settings, This will have a detrimental effect on the performance, the reliability, and the economy of the engine.